So welcome to this session on the Austrian Blockchain Center. I'm happy to be here. I would also like to thank the organizers for having us. We're happy to talk about our new research center on blockchain and related technologies, about our project scope and research outlook. So I will quickly introduce our center and tell you what we do, and then I will hand over to our researchers that will talk in more detail about the research that we plan to conduct at our center and that our partners have already done. So Matthias will talk about his and RIAT's role in ABC. Then Franz will give you an insight into our research area 3. And finally, Matteo and Philipp will talk about 2 individual research projects. So what is the Austrian Blockchain Center? So we are one of 25 so-called COMET centers, which stands for Competence Centers for Excellent Technologies. These are institutions that conduct cooperative research between academia and industry and are partly funded by the Austrian federal government and participating federal states. They are separate legal entities with a focus on building up competencies. So it's not just a consortium where resources and know-how is distributed among the partners, but actually the goal is to have research centers where experts in blockchain and related technologies conduct research and build up technology. So what is our mission? Our mission is to be a one-stop shop for blockchain research and development. And the goal is to advance the application of blockchain technology in many industries, for example, financial and the energy sector, logistics and retailing, government, but also industry 4.0 and Internet of Things. We are a consortium of scientific partners, company partners, and also associated partners like financial market authorities. And we plan to do basic research as well as application-oriented applied projects and develop use cases, prototypes, and proof of concepts. We have started our first funding period now on October 1st. So we're in operation now. So what are our partners interested in? We conducted a couple of months ago a study with our company and associated and scientific partners. And the results we got is that I think it's not that surprising, but many of our partners are obviously interested in questions related to identity, know your customer, especially in banking, supply chain, and logistics is an important area where research is important. Government, IoT, cryptocurrencies, but also manufacturing, which is part of Area 3, where Franz is our area lead. So as I said, we strongly believe in interdisciplinary research, especially in this blockchain area. So we have participating scientific partners from many different research areas. So it comes from technological experts in cryptography, internet security, which comprise our area 1, and really goes to lawyers, business professors, etc. So we have 5 areas. As I said, area 1 focuses on the more technological side, mathematics, cryptography, internet, and technological security. Area 3 is where I, as a financial economist, fit in well. So we are interested in business application of blockchain technologies, but also economic concepts like incentive structures in blockchain networks. Area 3 focuses on emerging industries and blockchain in manufacturing. Later on, Franz will give you a more detailed information about this area. Then we have an area that tries to utilize the data that is made available by having blockchain solutions. So area 4 focuses on data science methods for blockchain analytics and predictions. And finally, what is new for competence centers like ours, because most of the other competence centers in Austria do not have law professors involved, but blockchain really opens up a lot of research questions for our lawyers. So we have professors that do research on GDPR, tax law, and also company and corporate law. So we have a whole area dedicated to all these questions that arise when you want to do an ICO, issue securities, but also data protection and all the stuff that is important for blockchain applications. So with that, I would like to end the short introduction. So I'll be available in the break if you have any more questions about the center. Also my colleagues, if you want to talk to us in a bit more detail about our research program. And I would like to hand over to Matthias, who will tell you more about RIAT and his role in ABC.
Yes, hello. Thank you very much. Thank you very much, and a warm welcome from my side as well. My name is Matthias Tarasiewicz, and I'm part of the RIAT Institute for Future Crypto Economics. To explain you a little bit why this is important, because we are also a partner of this center. So me personally, I'm a research designer, project developer, and also technology communicator. I have a diverse history in technology projects and in tech. I'm also running or leading the Area 4 together with my colleague Bernhard Haslover from AIT. And I'm also director of the RIAT Institute. So we're an NGO existing since quite some time. And I will explain you also why this is relevant in this context. I'm also a board member of the OSHWA, which is the Open Source Hardware Association. So we're trying, with the OSHWA, it's a 501c3 in the US, we're trying to be like advocating and explaining the necessary use case for open source hardware. So we're trying to explain why this is necessary and why this could actually be potentially interesting also in the blockchain context. So you can get in contact with me as well. Here's my LinkedIn, Keybase, email account in case you want to discuss one of the topics I'm touching today, because this will be a rather short and fast slide through what I want to tell you. So the RIAT Institute is an NGO. It exists since 2011. It's actually one of the oldest blockchain-related research institutions to my knowledge. We have offices in Vienna currently in Austria, and we have a small R&D unit in Cyprus. And we are involved with a lot of international decentralized work groups around the globe, like participating in different protocols and so on. Basically, this is an interesting element I'm often showing. This was a kind of an infographic we have developed in 2018. And in my opinion, this shows two things very nicely. Firstly, that in Austria, there was actually blockchain and these affiliated technologies from a very early in time already active. So we have in 2011 already meetups started, things started to happen, and you can see also interestingly how this evolved over the time. Of course, we know that, and we know also that there was the hype and crypto winter and so on. But what secondly is important, and this is what I'm always pointing at, is that a lot of these developments, a lot of the research, and a lot of things that happen in the blockchain space, in the larger crypto economic and cryptocurrency area, is actually introduced by people who are not really affiliated to universities. So it comes from these fringes. It comes from very informal communities. And this is why you also see that we outlined here in this graphic a lot of meetups and informal structures that are somehow defining the discourse in blockchain. I find this very important to say because, of course, also if we look at Satoshi Nakamoto or the possible Satoshi Nakamotos, they wouldn't necessarily be in universities, if you get my pun. Publications and communications about from the RIAT Institute, and this is also relevant in the context that I've been telling before. So I was always fascinated by what kind of very high quality of research can actually come from the fringes, from not so formalized cultures. So this was my start into the whole area with a book I was co-editing with two colleagues, which was called Coded Cultures, New Creative Practices Out of Diversity. And we were, by that, tracking a little bit the fringes between art and technology and hacker spaces and hacker culture and technology. And for me personally, this continued with a book, and my research went into cryptocurrencies as distributed community experiments, which was a chapter for this book, for the Handbook of Digital Currency in 2014. I think the book was released in early 2015. And here I was actually fascinated, and maybe also to contextualize, this was in a time in the so-called golden age of the altcoins, when Ethereum didn't have its ERC20 tokens yet, the DAO didn't happen, so a lot of things didn't happen yet that we are considering normal. So this was interesting to me to see like how different experiments have been started in a decentralized fashion, and how value got attributed to all these kind of different tokens and how people were actually experimenting with all these different network parameters. This has been heavily changed after Ethereum, in my opinion, but for me this was also an interesting point to understand this a little bit more decentralized and more from a hypothesis perspective of this kind of value propositions that decentralized communities have. And my research then continued over more looking into cultures which are open sourcing things, so the open source models or business models of different open hardware communities. In this context, we also edited a book, which is interesting in my opinion, because it was actually looking at specific cultures that were open sourcing hardware and why are they open sourcing it, what is the context. And this is a more recent publication that we have been doing. It's called Future Crypto Economics. It's a magazine which is ongoing, so it has a lot of interviews, edited interviews and essays in order to find out what could be a potential future society which crypto economic principles have. Is it like positive, is it negative, is it a dystopia, utopian situation? So this is an ongoing thing of our institute. And mainly to explain more in detail what the institute does, so we do mostly research and development in these three fields. So we are heavily active in open source hardware, we do blockchain security, and we are also active in the field of privacy and anonymity. And maybe to give you a little bit of a context what that means. So this is maybe a well-known, I don't know if everyone knows this, very large open source hardware project where we have also been participating at. It was actually a European Union Horizon 2020 grant that we were writing. And basically this is a fully open source hardware available cinema camera. It's actually interesting, the project is now as old as Bitcoin, so it's like 10, 11 years, so it's actually interesting how these kind of things are possible. For me, this was always fascinating that these kind of things are possible to open source. And this is something we also are looking at with RIAT. So we are looking into strategies of openness, so how, what kind of benefit do you get when you open source things, what kind of problems do you run into, but then also we're looking into potential business models for open hardware, which is kind of an unsolved situation. There's always these terms of circular economies. This is an interesting point to research at, and we're looking into actual projects that work mostly with cryptography and hardware, and there's not so many open systems, although you would think that there's a lot of verifiable hardware out there. It's not. So this is the open hardware part that we're doing in RIAT. Blockchain security is also one of our, I would say, more applied approaches that we have, and the more we have a lot of projects where we actually look into specific projects or do some tech diligence for specific projects. This is maybe where you have heard about us before. So there was the Ethereum Constantinople upgrade, and my colleague Ralph Pichler, together with Chain Security, found a vulnerability. So this was actually in the news, and Ethereum couldn't really fork that good. So this is actually interesting, and you can read up about this more in depth at the Chain Security blog post. So we're looking a lot into different protocols. We try to understand parameters of distributed security, and we do a lot of code reviews, security reviews, but also tech diligence, and we have strong international partnerships in this regard. So this is also one of our key fields. The last field that we are actually, I would say, very active at is privacy and anonymity, the larger field. I know it's a large field, but here more concretely we work very closely with the Monero project. So we also run the meetups in Austria about Monero. We're trying to communicate a lot of the research findings of the Monero context on the Monero landscape, and we're also looking into layer 2 solutions and concepts in this regards. In this context, I want to also point to an event which will be happening end of the year, which we are doing now for the 4th year, I guess. It's called the Critical Decentralization Cluster, which is an infrastructure at the Chaos Computer Club, the annual meeting of the Chaos Computer Club in Leipzig. There are over like almost 20,000 people meet to basically hack and have fun with technology, but we more concretely implement a stage, and this is actually and a kind of a hackathon situation. This is done in cooperation also with RIAT, FOSS Asia, Decentrum, Monero Community, the Open Source Hardware Association, then the Parallel Polis, the Institute for Crypto Anarchy, and a group called Swiss Crypto Economics. So if you're interested in reading up on this or to join us, it's under decentral.community. Also, because I had very little time, I didn't want to go too much into detail what we are doing. So I can also recommend 2 recent talks I've been giving. One was titled The Past, Present, and Future of Opt-out with Open and Libre Hardware at the Hackers Congress Parallel Polis, HCPP. This is online already. If you're interested, you can watch it. And another talk I've been recently giving at the Ethereum DevCon, which is called The Future of Open Hardware in a Verifiable Decentralized World, like looking into how open hardware can also benefit for decentralized systems. And I want to also point to a meetup which will be on Saturday, November 2nd, where I'm honored to be speaking alongside Adam Beck and David Chaum. This will be actually here in Athens. I forgot where it is exactly, but I guess you can find this out online. It's organized by Blockchain Greece, and there we'll have a little bit more time to talk about like research details that will be happening. Thank you very much, and I will pass on to my colleague Franz Fidler now. Thank you.
Okay, welcome also from my side. I'm going to present you a little bit about blockchain in emerging industries, the industry's perspective. My name is Franz Fidler. I'm academic director of the University of Applied Sciences in St. Pölten, Austria. What you see here is that Austria has a continuously growing ecosystem within the blockchain landscape. These companies, startups, research partners, they are all heavily interested in the technology itself. But what this image misses out is all the players in the industrial field whose core technology and core products are not around blockchain or DLTs and these kind of things. In fact, the industrial sector in Austria accounts for 22% of the gross domestic product of Austria. To give you a comparison, within the European Union, it's 19%. So it's pretty significant for the Austrian economy. And while blockchain is not in the very well center of interest for these manufacturing companies, they are all very aware of that digital technologies itself, maybe including blockchain, will play an important role for future digital manufacturing, or as you all might know it, the Industry 4.0. And this is why the Austrian Blockchain Centers and also the university I'm working at partners up with large networks of manufacturing partners to tackle their research problems. And we have three main networks that we are working with. The Smart Engineering Partner Network that consists of 60 industrial manufacturing companies, also including some worldwide leaders in the field of the automotive sector, even aerospace sector or mobility sector. We have two other networks, 150 economic manufacturing partners within the network of the Future Academy, and then we are now building up this new network within the Austrian Blockchain Center. So what is the industry perspective? They are heavily interested in process innovation. And the challenge with blockchain technology, with DLT at the moment, is that we see a large amount of things going on with respect to product innovation. And when we do a survey with our manufacturing partners, they still see a large investment risk and they still see a large risk of obsolescence because of these product innovations and because we are not that heavily into the process innovation state at the moment. The challenges range from interoperability, which is missing, to many other things, and they reduce the potential benefits these industrial partners see. So to put it in a nutshell, the standards are missing, and that's their main problem at the moment. That is where Area 3 of the Austrian Blockchain Center comes in. We want to research semantic and technical integration of blockchain technology under the premise of A, standardization, and B, highly optimization of economical aspects. I just briefly present you here on this slide our general model that is put into our research questions. As I spoke before about process innovation, every step in these manufacturing processes has to be researched with respect to the potentials within the field of blockchain and DLT. This starts from the requirements, specifications, to the ordering process, then the manufacturing processes themselves. There are also some very important stakeholders in this field that are not directly involved, but have to have an eye on all that, which is auditing, inspection, certification. Then, of course, the logistics and delivery part. And it doesn't end there. It's also important in connection with IoT on monitoring the operational data of these future products and also the end of life of these products. And if you see here that we have several copies in this research model of these network nodes, which can be engineering partners, even single machines that manufacture something, or a simple delivery truck. We have to have a look at these topics from different angles. There is, of course, the flow of information, but then there is the flow of transactions. Then we have the material flow, and then we have many other flows that have to be addressed and are not necessarily in parallel when they have to be combined on a blockchain decentralized database. So the most important projects we are tackling now are firstly on the definition of semantic ontologies to get knowledge and building blocks which enable these companies to set up their smart contracts. These projects are also used to add another layer to the machine-to-machine communication layer, which is well standardized and defined. You know probably of developments like IEEE TSN and OPC UA on different layers, but still there are a lot of challenges when it comes to this blockchain economic layer. Digital twinning, which uses blockchain to link the real world of real products, of real processes to the virtual twins in the digital space, and one project that also tackles anti-counterfeiting measures for these manufactured goods. It's always the question, why does research also look into standardization? We have to give some guidance to these manufacturing companies and also be very at the right point in time in order to do the research, which then gives results for the standardization bodies. And here I show you an image where our research is situated. So we have the basic research and the oriented basic research mostly for the semantic standards, which then leads to the reduction of information cost and also reduction of cost in the transaction and the material flow. But we also have very applied research projects, which then rather tackles interfacing standards or even first prototypes, experimental development. And these significantly reduce the interoperability risks that these manufacturing companies see now and saves also in the adaptation costs. If you wonder what are the three main questions these industrial partners ask a research institute, the first is, should I use a blockchain? And it's not on a research institute that we sell some products or give some hints on which is the best DLT solution. We rather want to really assess the different methodologies that are out there in order to judge whether blockchain or DLT is a good solution for this exact use case or not. And the research questions are rather centered around that topic. The second question most often asked we get is, do I have to use a smart contract for my automated processes? And as you can see here on the left side, I just show one methodology that is given in literature, and on the right side I can show you where it fits into our generic research model. So we first have to define the requirements, as I told you before. Then it's always that within these networks that we have the identity problem, then to define the terms of the contract. And what we don't need to forget is that in the end, also the outcome of this transaction and the success of the manufacturing processes or of the logistics processes, they have to be measurable. And that's something that's often forgotten within this field. The third mostly asked question is the legal aspects. And I just show you that not because I'm an expert on the legal side, I'm in electrotechnical engineering in fact, but the Austrian Blockchain Center has an own area where we then, with like a transdisciplinary research approach, can bring in experts and they can give their knowledge and put the knowledge into these research projects if something is okay from the legal side. The most often asked question at this point in time from the industrial partners is with respect to GDPR regulations and what you can store in a decentralized database and what not. Okay, so because I'm running out of time a little bit, I just want to explain you one example project. This is about semantics and semantic ontologies. We have a number of researchers at our university that are experts in this field. And the statement that is made in semantics research is not new. First, if you have data that is distributed about numerous institutions, you have to have a common interpretation for the data. So semantic ontologies allow for better data standards, and they aid with the formal verification aspects if you have the data. And the latter definition is clearly something that fits perfectly into a smart contract as well. So we don't invent the wheel. What we do is we just look into these semantic ontologies and the models that are behind that. And this is a good way to implement smart contracts on a blockchain basis. You see here a simple example of a supply chain where we have the traceable resource unit, which are the goods of this company. The primitive activities in this ontology, they are the single nodes within the supply chain. And each node in the supply chain can then firstly consume this entity, this true. Then it does something with it, which means that it uses it. And then it puts it to the next node, which means that it produces the new identity. And all these things are linked together via a smart contract via this primitive trace. Okay, that's it from my side. Thanks a lot. And if you have more questions, I'll be happy to help you in the break afterwards. Thank you.
Hello, everybody. I am Matteo Romiti from the Austrian Institute of Technology, as we are one of the partners of the Austrian Blockchain Center, and we will focus on the analytics part, so data science and analytics. And in the next few minutes, you will have a look at GraphSense, which is an open source platform for analyzing and understanding cryptocurrencies. And I think the best way to understand what GraphSense does and what you can do with it is directly jump into it. So this is a screenshot of the platform. And you can see the currencies that we currently support. So Bitcoin, Bitcoin Cash, Litecoin, and Zcash. So very similar to Bitcoin in some aspects. And maybe you cannot see it directly, but there is a search box where you can input a Bitcoin address, a Bitcoin transaction, or a block. And this is like a standard explorer where you can see what happens in the Bitcoin blockchain. But one of our efforts at GraphSense is to allow you to understand what is happening in Bitcoin from an entity perspective. So when I talk about entity, I mean an exchange, a mining pool, a hacker, or malware. So different entities can do different things, and we want to understand what they do and how they behave and how we can improve a Bitcoin or any other cryptocurrency with analytic tools. And so another aspect, another input that you can enter there is a tag or a label. And a label is just a word like Coinbase or Binance or Bitfinex, so an exchange, for example, and you can look at the transactions of this entity. Another example that we usually use is, for example, a ransomware attack. Maybe you have heard about Loki, which is a ransomware that was launched a few years ago. And if you enter Loki there, you can see this. And what is this? This is the dashboard of GraphSense, and it allows you to understand where the money is going and who gets the money and what do they do with the money that they receive through the attack. You can see the Bitcoin addresses related to this ransomware. You can see the activity period, the transactions, and number of addresses, and you can also follow the money. So this is a first example that we always show, and this gives you an idea of what you can do. Of course, GraphSense is not only this, but this is just an idea. Now, what's next? In GraphSense, this is the architecture that we have. And you can see on the left side, we have open source and public data that we gather. So for example, we have 4 different blockchains. We fetch the exchange rates between Bitcoin and US dollar and euros, and the attribution tags. So when I was talking about Binance, Bitfinex, or Loki, so those are attribution tags that allow us to link one or more Bitcoin addresses to real-world entities. So this public data is ingested, transformed, and stored into our Cassandra database, and then we can query this database through a REST API, and you can use the dashboard, as you already saw at the beginning, or you can use any other scripting language. We have a R package that you can use to query this information, and you can do any analytics you have in mind. You can do research with it, and this is what you can do. Of course, you might have any new ideas, but this is what we already did and what we are doing. So different use cases. Law enforcement agencies are using GraphSense in their investigations. We are using it for research purposes, but there are many other interdisciplinary fields. So compliance with GDPR regulations are a hot topic now. Market understanding, and we try also to improve the design of Bitcoin with scientific research. So it's a mix of topics, and you are welcome to use it to find new ideas and to solve new open questions. One example that I can give you for research, that this was work that I did, and we were looking at the centralization of mining power in Bitcoin. So you maybe have heard about Bitcoin mining pools or mining pools in general, and you might think, oh yes, there are many mining pools and they all compete with each other, so it's decentralized. Okay, let's see exactly how much they are decentralized or centralized. And during this study, we discovered that it's not that decentralized. So for example, if you look on the x-axis, you have the time, and on the y-axis, you have the percentage of blocks mined by each pool, and the colors represent each pool, mining pool in Bitcoin. And you can see that the red line in the middle is 50%, which is an important threshold in most of the cryptocurrencies. And you can see that usually 3-4 mining pools, they control at least 50% of the hash rate. And if you dig a bit more into the details of these mining pools, 3 of them are either controlled or influenced or financed by one company, a Chinese company which is called Bitmain. So is decentralized? Yes, but not as we would like to. So this was one first example. I already talked about an example of ransomware, which was Loki. And another study that we did a few years ago was looking at the revenues of these attacks. And every day, every week, I guess you hear about oh, this city is now blocked because of a ransomware attack. They have to pay hundreds of thousands of US dollars, otherwise they cannot continue working. And this is still happening. And most of them are using Bitcoin or maybe other cryptocurrencies. So in this study, we analyzed the amount of money they made. For example, this is Loki on the left and Samsung on the right. And you see that 8 million US dollars was the revenue for Loki. And the next and last example is about sextortion. Maybe you have heard about this term, or maybe you just received an email saying, I have compromising material from you, and if you don't send me 1,000 US dollars to this Bitcoin address, I will release this material to your contacts, and it will be very bad for your life, so pay me. And we managed to collect 4 million emails of this type. We took the Bitcoin addresses and we tracked the payments and the money they received. And of course, we do not have a complete view in the entire world. We only have 4 million emails, but we suspect, and we are quite sure about it, that there are many more emails that we didn't find, that we didn't collect. And so this is just the beginning. And you can see that in few months, 6 to 10 months, they made more than 1.3 millions in US dollars as revenues. And yeah, so this is the last example of our studies and analytics part. And if you are curious about our work, is, as I said at the beginning, is open source. You can follow us coding on GitHub or on graphsense.info. You can see the papers that we publish and the work we do. And yeah, this is from my side the analytics part. And I hope you will be interested in this and maybe collaborate in other projects in the next months. And I think it's an interesting technology. And it's an interesting mix of different fields. So looking forward to working with you. Thank you.
Nice talk, thanks. A warm welcome from my side as well. I'm Philipp Schindler. I'm employed at SBA Research, and I'm happy to present you one of our joint research projects with my colleagues Alyosha, Nicholas, and Edgar. It's a quite technical topic, so I will start it slowly. To give you the idea, probably most of you have never heard of the term what a randomness beacon could be. So I start with an example. If we look at this kind of pseudocode on the slide here, we can see that obviously 4 might be a good dice roll, but if you say to a computer, give me a random number, 4 is probably not a good answer. So this is fairly easy to understand. And from here on, I want to explain what is the concept of a randomness beacon. So if you consider rolling a dice, and you watch me roll a dice, you can be pretty convinced that if I actually roll a 4, it was kind of a random process. You have a probability that rolling a 4 is happens approximately once every 6 times. So you can be somewhat assured that this actually was a fair dice roll. But if you consider a larger distributed system, like a blockchain or traditional Byzantine fault-tolerant systems, we have computers all over the world. And if I now, with a computer, roll a dice, I need to convince the other computer on the other side of the world that actually my dice roll, picking the random number, actually happened at random. And this is what randomness beacons try to achieve, to actually prove that the random number was determined using a random process. So this is the first step. What is a random beacon? Now I tell you why random beacons are important, and then I continue with a few approaches on how you can actually build one. Oh, this was the wrong direction. Let's go here. Why randomness beacons are so important. If we consider just the blockchain applications, we have, for example, smart contracts. In smart contracts, like you used to them in Ethereum, every execution happens in a deterministic fashion, which means you cannot rely on any kind of randomness there, because every step has to be executed the same way on all these different machines in the network. So what do you do if you need actual randomness for your application? Now, you're basically limited to using insecure sources of randomness. For example, a lot of gambling services nowadays use randomness derived from the hash of the Ethereum block. But as like bets get higher, in the end, your random number is just as secure as a single block in Ethereum. And a miner can just like manipulate and try different kind of values and can bias the randomness. So what we want to actually build is a protocol which kind of prevents these kind of attacks. So smart contracts are one particular use case. But even on a more fundamental level, if we consider like traditional Byzantine fault-tolerant protocols, there's in an asynchronous system model, for example, there cannot be deterministic protocols. So fundamentally, you need cryptographic randomness for all these kinds of protocols to work. If we want to replace the power inefficient protocols which are used, for example, in Bitcoin or Ethereum, which depend on this cryptographic protocol of the mining process, actually there you see this is a random selection process, which basically the mining during this kind of process selects one of the miners at random to build the next block. So you have this random selection inherently in most protocol designs. And if you actually want to get away from like using this very energy consuming process of mining and replace it with some other things, you need this kind of distributed random speaking protocols. Another very interesting use case is sharding. As most blockchains are built now, every node in the system runs everything. So basically, each computation step is executed at all nodes simultaneously. And what a lot of scalable blockchain designs propose is actually that you have multiple kind of blockchains which are somehow linked, but like executed in parallel, independently of each other. And the key problem with those approaches is that now you split up your security guarantees onto each of the partial chains. And what you can do with randomness is you can leverage like a randomized selection on who actually is responsible for which of the partial blockchains. And there, if you assume that say 50% of the overall network are honest, and you pick randomly some parties which are then used to mine on the one chain, and pick randomly a bunch of people who mine on the second chain, if you make this random selection proper, then you are ensured that approximately 50% of each of the groups are themselves, again, 50% honest, just by using probability theory and like proper parameters. So for sharding, randomness is also a critical component. And even outside the whole blockchain sphere, there are a lot of use cases ranging from, I don't know, e-voting protocols. It's used in Tor for anonymity services. And like there are lots of other applications even outside the blockchain space. And now that we know why we need it, I show you a few examples on how you can actually make it. But before, I want to quickly introduce what we actually want to achieve. So there are a few properties which kind of one expects from a random number. So for example, a random number should be unpredictable. I shouldn't know what is the next random number before it's actually like computed or revealed. So this is called the unpredictability property. Of course, like if I just would say, okay, our random number is the digits of pi, the digits of the comma in pi, then of course they look random, but they are totally predictable. So this would not be a proper randomness speaking for this purpose. And other properties are like energy efficiency, of course. If you want to get rid of proof of work, we better build a solution which doesn't require mining effort. Scalability, we want to distribute it, support a large number of nodes. And there's a few other nuanced properties which are, for example, bias resistance. And bias resistance means that these random numbers are computed like using multiple computers around the world. And bias resistance means that none of the parties should actually be able to influence the properties of the random numbers. So this means the random numbers, for example, should be uniformly distributed. And like you shouldn't be able to predict what is the last bit, or you shouldn't be able to bias the last bit towards a 1 or a 0. All of these kinds of attacks shouldn't be possible. In the end, you want a perfectly randomly, uniformly derived random number. And the public verifiability part is actually the critical property here. You want to be able to convince somebody else that the computation of which resulted in the random number is actually secure. So that other people can verify, as you now can verify, for example, the Bitcoin blockchain. So I want to go into 4 different methods on how you can use this. They're quite technical, so yeah, I try my best to break it down to the essentials. And if you have like more in-depth questions on any of those, I will be happy to take them afterwards. So the first approach is based on what is called secret sharing. In secret sharing, you have some kind of secret. Think of it as a private key, which you want to share across multiple stakeholders. Say in this case, it's 5 companies. And you want to share this secret in a way that any 3 of those 5 companies can come together and then reconstruct the secret. And it really doesn't matter which of the 5 parties come together. As long as there's 3, they can compute the original secret. And this is like a building block used in kind of this random number generation process. And there is even like a more nuanced version of this, which is called publicly verifiable secret sharing. And the key difference here is that in a traditional secret sharing scheme, which was already invented in like 1979 by Shamir, is that you trust the person, the single entity who shares the secret in the first place. So if I share a secret with everybody here, actually everybody needs to trust that I shared it correctly. Otherwise, the reconstruction phase, where you kind of a group of you comes together and reconstruct the secret, doesn't work out. And what newer protocols, for example, simple in relative terms, is called the Schoenmakers PVSS. And this protocol specifically is able to kind of prevent this issue of you all having to trust me as a dealer of this secret sharing protocol. So when I give you the shares, each of you can check that the shares of the secret I give to everybody are indeed valid. And you can do this even for the other people. So you can check that all the shares I give out are valid. And this is like a crucial property we need to actually achieve this public verifiability property in the overall protocol. And if we have such a secret sharing protocol, which they're actually quite common and well established in the cryptographic community, we can have a very simple process to actually kind of make a random beacon protocol. It's not very efficient, but it's like the first step towards an efficient approach. So what's crucial here is that there are a few steps, but these steps are executed by everybody who's willing to participate in like computing this random number together. So let's say we have 100 parties, whatever people in here, and we want to compute these random numbers together so that nobody of us can manipulate the results. Then everybody of us does the following 3 steps. So in the first, I share a random secret with everybody else, and you all do the same. So you all share, again, a random secret with everybody else. And in the end, we try to combine all these random numbers together, and we get a random number which is actually totally random and cannot be biased by anybody. So the first step is everybody shares with everybody else, which is inefficient, but works for now. Then the second part is we actually need an agreement, because maybe some of you didn't share. And we need to agree on who actually shared and who actually shared what with everybody. And if you use, for example, a blockchain on this, you have all this data in the blockchain, and the blockchain gives you the agreement on how you get these values. And then there is the final step, which is like everybody just reveals the random number which he previously shared. And if everybody reveals, we can just basically add all the numbers up. And if we add random numbers, which are independent of each other, as long as one of those random numbers was random, the result is random. So if I add 1 to a random number, it's still a random number. Basically, this is the idea. And the crucial point is, some people might not publish their things. So you cannot, if somebody has a secret, you cannot force him to reveal this secret. And this is the crucial point which a lot of protocol designs actually miss. And here the secret sharing protocol comes in. Because like if I'm not revealing my secret, then you can come together and reveal my secret instead of I'm doing it. So in the end, we get the same result, and it's completely like you cannot manipulate the result. Because if I'm not doing it, everybody else can do it instead of me, together. And this is like the very high level approach on how these PVSS-based beacons work. What we did actually is a kind of more advanced approach of this. We kind of interleave, like doing a pipelining approach of these first simple steps. And we can actually show that we can reduce the overhead of the protocol, and not everybody needs to share with everybody, but only like one person needs to share with everybody else. So we kind of reduce the communication a lot, and we can actually show that we can like come up with random numbers in like a few seconds, basically, in intervals of a few seconds consistently. We tested up to 128 nodes across the whole internet. Yeah, in practice it looks a bit more difficult. So this is a flowchart of how the protocol actually internally works, but I have not the time here to go into the details of how this works in practice. Another approach which is particularly interesting for smart contract applications are so-called verifiable random functions. A verifiable random function, basically, you can think of it as a digital signature, which for every public key there is only one valid signature. So you have an input. In this case, it's called the seed and the round number, and you have a secret key, which some party which wishes to run the verifiable random function knows. And using the seed and the round number, the result, which is written in uppercase R here, is guaranteed to be a random number, as long as like you cannot try multiple times. So if you have a single input, and then the result is secure and bias resistant. So this can be, for example, used in a gambling service. Imagine you have a lottery in a smart contract. You get a lottery ticket, and in the end, if you decide basically the seed value for this lottery ticket, and all the lottery has to do is compute this verifiable random function, get the result on the blockchain verifies the result, and you have a perfectly random number, and that's fine. This is also used in the protocols Ouroboros and Algorand, for example. Then there are Then there are verifiable delay functions. They are quite new, introduced only in 2018. These are also like cryptographic primitives, similar to the verifiable random functions. But they actually, what they do is you have a function which takes sequential time to compute. So you put some input, like say the hash of a block, into this verifiable delay function, and then you compute the verifiable delay function, and this computation takes time. And in contrast to mining, the time it takes doesn't depend on how much you can parallelize the approach. So you have kind of this fixed time, how long it takes to get to the result. And if you have an agreement on the input, for example, using a block hash, and you compute this verifiable delay function on top of it, until you are finished with the computation of the verifiable delay function, the block in this example in the blockchain is already like buried and like confirmed multiple times, and therefore the output you can use as random number, and yeah, basically without being able to manipulate it in any way. So this is a very simplistic idea how you can use verifiable delay functions for the purpose. And verifiable delay functions are also considered for the new Ethereum-based proof-of-stake approach. The difference here is actually what you use as the input for the verifiable delay function. If we say here the input is a proof-of-work blockchain, of course I cannot get the benefits from like replacing proof-of-work with such an approach. So again, we kind of need to find an agreement on what we actually put into the verifiable delay functions in the first place. And this is the difficult part. And the last approach I want to talk about briefly is using unique threshold signatures. Unique threshold signatures are useful for not only this approach for generating random numbers, but they all have use cases in like compressing certificates or compressing multiple signatures into a single signature, which helps with efficient verification, for example. So the idea of how you can use threshold signatures is, again, you set up a key pair, which is kind of comprised of, like we have here we have 3 secret keys. And these secret keys are kind of interlinked, and they are set up in a specific way. And how they're set up, they typically set up either using a trusted dealer, which of course is bad, or they set up using a distributed key generation protocol, which is also not that simple. So, but if assuming we have this setup, we can then, like, each party can individually sign, for example, a round number in the blockchain protocol, like say the height of a block. And if enough people come together, then they, as with secret sharing, if a group of people comes together, they kind of compute the signature, which can be then verified by everybody else. So only a subset of the nodes have to come together, sign the same message. Then we kind of put all the signatures together, basically add them up, and then we can check the result against the public key, which is again comes from the trusted setup or the distributed key generation protocol. And in the end, what we get is we check one digital signature, and we basically get the perfect random number. And the problem with this approach is we need this kind of setup, and can either do it trustedly or using a distributed key generation protocol. I'm skipping some details here. So here is a quick and very high-level overview summarizing the pros and cons of these approaches. All of the approaches have pros and cons. This is the crucial observation, which is also one of the results from our research paper here. So depending on the application you actually want to build, there is a different solution which fits best. There is no winner in every category, unfortunately, but it's pretty clear. For example, PVSS, you don't need this kind of assumptions regarding the setup, but it's more communication heavy than the threshold signature approach. And for verifiable delay functions, again, you have this kind of problem of how you define the input, but for example, they have very low communication overhead. So all of these problems, all of these protocols have advantages and disadvantages on their side. I'm not going into more detail at this point, but again, you can ask me afterwards, or you can have a look at our paper, which we published, will be published next year at the IEEE conference on security and privacy. And part of the paper, the first part of the paper is our approach using the PVSS, and the other part of the paper is a very detailed comparison about basically every protocol which was out there when we looked at this. Without further ado, there's a few, I think, time for 1 or 2 questions left, and afterwards I will be happy to be outside. My colleagues are outside if you have any further questions. Thank you very much.